We already discussed in the previous chapter about the basic principle of the electromagnetic wave, as well as how to write the expression of the wave in terms of the mathematical equations. Next, we will discuss what happens if the electromagnetic wave or the plane wave travel through the different media. We will discuss these four different media. Firstly, we have the lossy mediums, and then we have the free space, then the lossless medium, and lastly the conductors. So we only have these four different media. Let's starting our discussion with the lossy medium. First, for the lossy medium, we will discuss about the loss tangents. Basically, the loss tangent is a ratio between the conduction current density and also the displacement current density uh, JD. So when we solve this, we will got that the loss tangent equal to sigma divided by omega epsilon, like what we have proved in our previous chapters. And this loss tangent can also be represented by the tangent to theta n. Okay, we will see what is this theta n. Okay, indication of what medium we are dealing with. Okay, because different media have a different properties. For example, we have for the lossy medium, or we also said as a lossy dielectric. So we have the small value of sigma. When we have the small value of sigma, that means there is a leakage uh, conduction current. So it has a loss. When there is a conduction current, there is a loss. For example, the loss in terms of the heat energy. So for the lossy dielectric, normally we have the value of sigma, but the value is still very small compared to the omega epsilon. Okay, for example, we have the um, fire retardant 4 board FR4 that normally used to design the planar antenna. So the FR4 board had a loss tangent of around 0.02 or 0.02, something like that. It's very small. Next, for the good conductor, for example, we have a silver, copper, gold, and so on. So we have the sigma very large compared to omega epsilon. The sigma represent how well the electron can move inside the material. And lastly, we have the free space and lossless medium, where both cannot conduct electricity, so the sigma will be equal to 0. For the lossy dielectric or lossy media, so basically we have the value of sigma. Okay, the sigma is not equal to 0, and we have the value of mu. Okay, mu will interact with the magnetic field, and we have epsilon. Epsilon interact with the electric field. So we have mu equal to mu naught mu r, and epsilon equal to epsilon naught epsilon r. Okay, this is the general equation of the electric field. The E equal to in the direction of x, the E naught exponent negative alpha z cos omega t minus beta z. So we already see this expression accept this component exponent negative alpha z. So basically this component represent the lossy part, the lossy or attenuation. For the magnetic field H, okay, we have the direction is y and the magnitude is h naught, exponent negative alpha z cos omega t minus beta z minus theta n. Okay, we have theta n here and also exponent minus alpha z. So this is also the lossy component, and the theta n is basically the phase difference between the electric field and the magnetic field. There is a phase difference that we need to determine. And then we can find the magnitude of the magnetic field by using this formula. So it's basically the magnitude of electric field E naught divided by the intrinsic impedance N. So this is the magnitude of intrinsic impedance. We'll see later how to determine the intrinsic impedance. Okay, the intrinsic impedance, okay, N is basically equal to the surge J omega mu divided by sigma plus J omega epsilon. Okay, because the sigma has a certain value, so basically we have the theta n. Okay, how to determine the theta n is basically the ratio between omega epsilon and sigma, something like that. Right, so this is how we write the intrinsic impedance in terms of the magnitude and phase. Okay, and also in this form, the exponent is normally represent the phase. Exponent j theta n. So the tangent to theta n is equal to basically sigma divided by omega epsilon, because here we can find the theta, but the theta n is different. So tangent theta equal to tangent to theta n, and this is a loss tangent because we have a sigma, we have a loss tangents. Loss tangent equal to sigma divided by omega epsilon. So that's mean if the sigma is 0, so the loss tangent is also 0. So there is no loss. Right, for the lossy media, when we excite the electric field, what happened? So from the original uh, amplitude, so when it travel further away inside the lossy media, so the attenuation happen in the form as exponent minus alpha z. It's travel um, through the distance. The further distance, so the attenuation will be greater until it become 0. Okay, so this is a velocity equal to omega divided by beta. Beta equal to 2 pi over lambda. Okay, this is just a simple expression that we already discussed before. And then the lossy media for H component also the same. We can see that um, the amplitude also becomes smaller as it is attenuated when travel inside the um, lossy media. So the pattern is the same, but we can see there is a little bit different in terms of the phase. So the difference is depend on the value of theta n. So what is the theta n here? How to find the theta n? Here is the amplitude. We can determine using the E naught divided by the magnitude of intrinsic impedance. This is the general equation that you have to understand and remember. And this is how to determine the propagation direction. So this is a AK or AP, the propagation, and this is the direction of the electric field, the E field direction, and this is a H field. So please stick to this equation to overcome the confusion, because later on I will show you that the slide using the slightly different expressions. Right, so we will discuss the attenuation factors phase constant as well as the propagation constants. When we go back to the general equation of E field and H field, so we can see that there is a value of alpha as well as beta here in both electric and magnetic field. And in this expression, the propagation direction is z, but it can be different depend on the question that we deal. So the alpha can be determined by using these equations. We have the omega set mu epsilon divided by 2, and in bracket the x the power of half minus 1. So the x here can be determined by using these equations. The x equal to 1 plus sigma divided by omega epsilon square. The phase constant beta equal to omega set mu epsilon divided by 2 in bracket x the power of 1 over 2 plus 1. So the difference is here is minus 1, here is a plus 1. The unit is also different. This is a Newton pole per meter, this one is radian per meter. The propagation constant is equal to alpha plus j beta. So you can see how we prove the equation in the study book. I will not discuss more about this, but please remember, please take note that there is a one final exam question in the previous years about to prove the alpha and beta. So hopefully something about the proving the equation you should take note. So we see the example related to this part. Okay, a lossy dielectric has an intrinsic impedance of 200 and the phase is 30 degrees ohm at a particular frequency. If at that frequency the plane wave propagating through the dielectric has the magnetic field of H equal to 10 exponent minus alpha x cos omega t minus 1 over 2x in the direction of y ampere per meter, and you have to find what is the E and alpha. So that is the information from here. This is a lossy dielectric. When we talk about lossy, it has a certain value of sigma, and the intrinsic impedance here is we have the N and the phase. Okay, and then from the equation of magnetic field. So here is a H naught. So you can use the H naught to find the E naught, and we have here the attenuation factors. So we have to define what is alpha, and here x means this is the direction of our propagations. This is the direction of our propagation, x, not z anymore. So this is the oscillating direction of H field is along y. That is the information that we can extract from the equations. So the general equation of E in a lossy medium, this is a general equations. Okay, so we have the E naught, the attenuation factors, and the cos omega t minus beta x plus theta n. So the E naught is basically equal to the magnitude of intrinsic impedance multiplied by H naught equal to 200 multiplied by 10, we got 2000. And then the theta n from the equation is 30 degrees. In terms of radian is equal to pi over 6. You have to change to radian for calculation. Pi over 6 is equal to 30 degrees. And here, to avoid confusion, you have to use the direction of propagation equal to the direction of the E field cross product with the direction of H field. Just use this. And then this is the direction you have to follow: the X, the Y, and the Z. No, the Z. Okay, this is the directions for the cross product. Just follow this. So we know about the direction of our propagation is from the expression. This is X, and H is basically Y. So what cross product with Y, we get X. The X is here, and our Y is here. So it's basically from here to here, right? So it's basically minus Z cross Y, because it's rotated to the another directions. That's why here the answer is negative Z. The loss tangents, how to determine the loss tangents? Okay, the tangent to theta n equal to tangent 60 equal to sec 3. And then we know the tangent to theta n equal to sigma divided by omega epsilon. Okay, equal to sec 3. From the previous solutions, the sigma divided by omega epsilon equal to sec 3. So we can use this information here. Okay, so basically this is the value of x, the power of half, because the x equal to 1. So basically, so x, the power of half is also 1. So this is 1. We put the value. So finally, this is the expressions we obtain for alpha, and similarly for beta we obtain these expressions. Okay, we have two expressions. Since we know from the equations, okay, here, this is basically the value of beta. This is beta. The beta is a 1 over 2. So we can use the information here. Since the beta is equal to 1 over 2, so we can determine the value of this part. Okay, this part. Okay, so this part, because everything is equal to 1 over 2, so this part is basically equal to 1 divided by 2 sec 3. We don't know what is omega, mu, and epsilon in this case, but we know the total is equal to this. Similarly, because we know this value, so we can solve for alpha. Okay, because this is 1, so it's become 1 over 2 sec 3. So we can put the value of alpha here. So minus 1 over 2 sec 3, and what's others? We see the general equations, or we have a beta. Okay, here we have beta and also theta n. So this is beta and this is a theta n. Okay, and the direction of E is in the direction of minus z. So we have here some minus in the z direction.